Welcome back to another exciting chemistry lesson. In the previous lesson, we learned how to draw Lewis-Dot structure. Now we are going to look at another type of problem that deal with Lewis-Dot structure, and that is isomer. Well, isomer are basically different structure of the same chemical formula, with atoms connected through the same types of bond, but with different orientation. Now, the type of bond we are talking about single bond, double bond, and triple bond because they have the same type of bond, and therefore their formal charge is not going to change, okay? So that's the beauty behind of that. We have to realize because they connect through the same type of bond, the formal charge is not going to be the same. Now, let's look at this. Now, how is this different than resonant? Well, in this type of isomer, the electrons are not delocalized. The electrons are now restricted to that bond. So before we're looking at specific example, there is one important information that we have to remember, and that is sigma bond in a single bond. We learned that a single bond is made of one sigma bond. And sigma bond is special because it allows the free rotation. What does that realize? What does that tell you when it's free rotation? Well, if it's continuous free rotation, there might not be an isomer. Now, in order to understand that, let's look at this example here. We have chlorine right here, which what makes the whole entire thing very different relative to the CH3 right there. Over here, we look chlorine is on top, CH3 is on the bottom, but here we have chlorine on the bottom and CH3 is on the bottom. Well, we thought this is going to be an isomer, right? Two different isomer. Well, it turned out, remember the sigma bond is allowed free rotation. This rotation is happening continuously. So therefore, this whole entire molecule is actually one single structure. They are not different structure. They are just a single structure. And look at this case where we have a pi bond. Remember we learned pi bond happens side to side overlap of electron, and this side to side overlap restrict rotation. So we have chlorine here, but over here we have chlorine and CH3 on the opposite side. Because of the double bond, we cannot freely rotate it, so therefore we have two separate structures, isomer 1 and isomer 2. And that is how sigma bond play the role in isomer. And now let's look at some of the example problem. Draw the structure formula of each isomer, including all atoms of C4H10. And we learned that C4H10. Remember with the Lewis dot structure, there are 4 and 4 plus 10 for 10 hydrogen. So therefore, in this case, 16 plus 10 give you what? And 4 times 4 is 16 plus 10, that gives you 26 electron. But in most cases, whenever you see like this is considered as a hydrocarbon. What's happening here is the carbon will be the chain, okay, like that. Okay, keep that in mind. And the hydrogen will be surrounding all of this right here, okay? 1, 2, 3, 4. So in this case, we have H, 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 and as you can see, this is a common pattern where we have carbon and hydrogen. This is what you usually see all the time. So count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. 4 carbon. Now let's check the electron. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 times 2 is what? Is 26. There you go. So this is one possible isomer. Now, remember, the key part of isomer is that we have different orientation, but the connection of bond needs to be the same. In this case, all of them are single bond. So that's pretty easy. If you look at this right here, see how this right here, CH3 part, we can move to anywhere we like. We can move to here, and then we can bring this over here. So now we would have something like this. Okay, so let me show it to you. I'm gonna move this over here, okay? So we have H, C, H. And that's what makes isomer so tricky, but easy at the same time. So you have C, so we switch the location, right? Remember, the bond is type is still the same, it's all single bond. So we have C, H3. There you go. And down here, just still H. The only thing we change is this part and that part. And here we have C, H, CH. Now this part, remember we replace it with that. We just switch location. So there you go, that is another isomer. Isn't that nice? Now just one thing that we have to be very careful with, remember this is a 3D structure. So just because it looks different on a 2D, let me show you this, okay? What if I switch this over here? What if I tap this like this? Is this two different isomer? So basically what I'm going to do is I'm going to switch this down here. Are they two different isomer? No, they're actually the same one. So this is not another isomer, okay? So be very careful with that one, okay? So double check your work again. Now let's do another one where we have C5H12. So in this case, 4 times 5 is what? Plus 12. So 20 plus 12 is what? Equal to 32. And now let's go back in. Remember, the pattern is always have carbon in the middle. Okay. We have 5 right there. And of course, this will be branching off to hydrogen. Isn't that easy? It's just a lot of work, that's all it is. And double check again. We have 5, 5, so it's 12 hydrogen, that's good. And then for the electron, we have 5. Then we have 5 here down here as well, so that's 10, 11, 12, 13, 14, 15, 16. So 16 times 2 is 32. So we have used all the electron. Now it's the same process approach, right? All you do is take one of the end, this end or that end, and switch place with one of the hydrogen. In this example, we are going to look at mistakes in terms of the isomer that might look different, but is not different at all because of the free rotation. And here, as you can see, I'm going to switch the CH3 with one of the hydrogen that's right next to the edge, right? Which is allow the free rotation, as you can see here. I have my CH3. Again, it looks very different, but it is not different at all. That's because you notice it's a free rotation that we have right there. So it looked completely like a different structure, isn't it? And here I continue, but what you notice right away, again, the free rotation right there is allow you to have completely different look, but again, this rotation happened continuously. So therefore, in the end, it looked different, but it's actually the same isomer or the same structure. So that's one thing you have to be very careful, okay? If that's the case, we switch with this one. So we have CH right here. Okay, so now we're going to the next one, which is C right there. And this has connect to CH3. And then what does it have next? We have C right there. And the rest of them stay the same, right? Because we didn't make any changes over here. Now let's look at another one where we have a more complicated example. In this case, let's assume we have CHC. And then there you go. Now we have connect to OH. And let's see how this will make our life a lot easier when we have a unique group like OH, right? Because of this unique OH, we can move to different places and it gives us a different isomer. So the best bet is to move in the middle. That way we don't have to worry about the different type of orientation, okay? Remember, this allows free rotation, so be careful with that, okay? Because this can be over here and that can be over there as well. So the best bet is to go in the middle. So in this case, H, C, H. So we switch the location OH and H, right? And there you go. By being safe, we put in the middle. Now we don't have to worry about there could be possible free rotation of sigma bond that make the whole entire two structure look different, but it's actually the same structure. By putting in the middle, we know for sure these are two different isomers. And that is how you apply isomer and Lewis dot structure. And as always, if you have any questions, take a picture of your work, put in the forum, and we will help you from there. And we'll see you next time on another exciting chemistry lesson.